Alright, good morning, good evening, good afternoon, or whenever you happen to be watching this video. Okay, so here we are for yet another lovely session of MENG 3310 Fluid Mechanics. Okay, so we have a few learning objectives for today, and let's take a look at these. So we're going to be in sections 7.1 through 7.3 of the textbook, and we have a few, and as I mentioned, we have a few learning objectives. So the first is to describe the need and benefits of similitude in fluid mechanics. Second, to define a non-dimensional parameter. 3, describe common variables and dimensional groups or dimensionless groups used for creating models. And 4, apply the process of repeating variables to determine pi terms. So let us first discuss common dimensional systems. Okay, so let's see what I mean when I say dimensional systems. Dimensional systems. So, what do you think I mean when I say dimensional systems? What might this entail? Now, there's a few common dimensional systems, and really all of our units that we've used up through the semester, and all the units that we use in physics, in engineering, etc., can be broken down into two main dimensional systems. There is the MLT system, and there is also the FLT system. And the FLT system. Okay, and the FLT system. So let's describe each of these, and let's see what exactly we mean therein. So the MLT system is going to be the mass, length, time system. Mass, length, and time system, where we consider the fundamental units to be mass, length, and time, and everything else is constructed from these. In the FLT system, we consider force, length, and time to be the fundamental units, and everything is constructed from these. Oops, helps if we write the correct length and time. Mass, length, and length makes a lot of sense. Alright, so let's work through an example with dimensions. So consider an example with dimensions here. Let's see here. So let's look at an example with dimensions. Okay, so let's say I want to look at the Reynolds number, probably the most important dimensional parameter that we'll see in fluid mechanics, and let's say I want to verify that the Reynolds number is dimensionless. That Reynolds number equals rho v d over mu is dimensionless. So how would I do this? Well, let's look at this both in an FLT and an MLT system. Let us look at this both in an FLT and MLT system. So in MLT and in FLT. And I apologize for the video issues. We're experimenting with a new software today. That a little bit different from the, because of where I'm recording this, I have a bit different software and equipment use than normal. Okay, so let us look at, for example, the MLT system. We'll consider the units in rho, which of course is density. Well, fundamentally, what units make up density, make up mass density? So with this symbol here, with the equal sign with the dot above, this is going to mean this is going to be referred to as not equal but dimensionally equivalent. So rho is dimensionally equivalent to m L to the negative 3. V, which is our velocity, is going to be dimensionally equivalent to Lt to the negative 1, Lt to the negative 1, because again this is velocity, which is, say, for example, meters per second, so a unit of length over a unit of time. Diameter is going to be dimensionally equivalent to simply length, and mu, our viscosity, is going to be dimensionally equivalent to m L to the negative 1 T to the negative 1. Okay. Now, let's say I combine these together. What would I get? Let's go and put these into the formula for Reynolds number and see what kind of units we end up with. So if I go and I put in each of these values, m L to the negative 3 for rho, times Lt to the negative 1 for velocity, times L for diameter, and divided by m L to the negative 1 times T to the negative 1 for mu, and I can find fairly quickly that this, well, let's see. Mass and mass are first going to cancel out. T to the negative 1 and T to the negative 1 are going to cancel out. And I clearly have negative 3, negative 2, negative 1, and negative 1. And I am left with Reynolds number being essentially completely dimensionless. It is m to the 0, L to the 0, or its dimensionally equivalent, to m to the 0, L to the 0, and T to the 0. So in the MLT system, it is dimensionless. And as we'll see in our later discussion of pi terms, dimensionless units or dimensionless quantities are very useful for studying fluids and other systems. And we'll see why that is important later on. So in FLT, rho will be dimensionally equivalent to, instead of looking at this in terms of mass, I can also look at this in terms of force. It is if you work through it, you'll find that it is dimensionally equivalent to F L to the negative 4 T squared. And that V, velocity, is dimensionally equivalent to Lt to the negative 1, Lt to the negative 1, and diameter is dimensionally equivalent to length. As before, that one doesn't change. The only ones that are going to change, notice the velocity and the diameter are not going to change. Logically, the only ones that are going to change are terms that have either an m or an f in them. And viscosity is going to be dimensionally equivalent to F L to the negative 2 times T. And if I do the same sort of calculation here, I can find that Reynolds number is going to be dimensionally equivalent to F L to the negative 4 times T squared for our rho times L T to the negative 1 for velocity, same as before, times L for our diameter. And then all of this divided by F L to the negative 2 times T for our mu. And then if we start canceling things out, well, F here and F here are going to cancel out. Let's see, well, this becomes T squared, and T to the negative 1 become T to the positive 1, and then T to the positive 1 here, these will cancel out, and then L to the negative 4, L to the negative 3, L to the negative 2, over L to the negative 2, and these cancel out as well. So I am left with the result that the Reynolds number is dimensionally equivalent to, I should probably have a dot over these, is dimensionally equivalent to F naught, F to the 0, L to the 0, and T to the 0. So when we say a dimensionless quantity, this is what we're talking about. We are talking about something that all of its dimensions, when you work through the units, when you go and work through the multiplication, division, etc., that go into the formula for that quantity, it comes to 0. And Reynolds number is often what we would consider the most important example of a dimensionless quantity in fluid mechanics. Alright, so let's see, we're still recording, we're good, everything's fine. Okay, so let's talk about dimensional analysis. What do we mean when we say dimensional analysis? You may have seen this on the syllabus before and been a little confused. What on earth might a dimensional analysis be? Dimensional analysis. Kind of a tricky thing. So let us consider a system, and say we have a smooth-walled horizontal pipe. And let's say that I want to measure some property of this. For example, I want to measure the pressure drop per unit length of this pipe. So we're going to have a pipe, and I'm going to be working through this example through a few slides here. So let's say we have a pipe, a smooth-walled pipe, and I want to look at the pressure drop or head loss per unit length of this pipe. And it's going to have a few quantities. It's going to have diameter d, and then it will have a fluid velocity, a v in here, and then the fluid properties will be mu, and it will also have a certain density rho. And what do we want to do? We want to we want to measure what I am going to call the pressure drop per unit length, which I will call delta PL. So I want to measure the pressure drop per unit length, or I don't just want to measure it, I want to investigate it. Delta P sub L. So, what do I mean by this? Well, so in other words, I want to investigate the head loss, and there's a certain pipe, and I want to, when I say analyze this or investigate this, what I'm really talking about is experimentally. I want to experimentally investigate the relationship between what will go in to the pressure drop per unit length of this. In other words, it's going to be some sort of function. I'm just assuming there may be other variables as well, but these are four that I want to consider. So I want to know what kind of relationship exists here, and I know that's going to be some function of, say, the diameter, the rho, the mu, and the v, and the velocity v. So just for, these are four common variables that affect flow, and I don't know what kind of relationship will exist here. So I want to run a set of experiments that that will investigate how this thing will work. Now, we could do this different ways. Now, have you learned from, way back in elementary school, even, or middle school, or even that level of education, you learn the very basics of the scientific method, and you learned how the fundamental, most elementary school level basis of the scientific method is form a hypothesis and perform an experiment, test your conclusions, have a dependent variable, independent variable, etc., etc., etc. So if I want to investigate this one variable at a time, what would that actually take? Well, if I wanted to have just one independent variable, I would have to, say, investigate d while holding rho, mu, and v constant. I would have to investigate rho while holding d, mu, and v constant, etc. So I would have to do a whole series of experiments, a whole mess of experiments. In each case, holding one variable constant while changing the others. While holding three variables constant while changing just one. That way I can have a clear relationship between one variable and the change in the delta PL. But as we can see, this is going to get very time-consuming. It's going to be very expensive. There's got to be a better way. I don't want to have, for real-world complicated systems where I can have multiple variables, affecting what I'm trying to measure, it's going to be very difficult, costly, and expensive to try to measure every single variable independently. So instead, I want to find a better way. I could develop the relationships one variable at a time. I want to use something different, and that method is known as dimensional analysis. So let's consider dimensional analysis. What is dimensional analysis? Well, fundamentally, dimensional analysis is going to be a method to combine variables into fundamental dimensionless numbers. I want to combine variables into dimensionless numbers like our Reynolds number previously. Variables into fundamental dimensionless numbers. And the nice thing about being dimensionless is that then they are also independent of our unit system. Well, independent as long as they're both. As long as in other words, I can substitute any unit for force, for example, and it should still turn out to be the same into fundamental dimensionless terms. Not dimensional, dimensionless terms. Into more fundamental dimensionless terms. Or for example, e.g. Reynolds number. Example, Reynolds number is an example of a, so again, Reynolds number is an example of a dimensionless term. It is the most, as I mentioned, it's the most important dimensionless parameter in fluid mechanics, and it comes from this process. And dimensional analysis, really, the point of it is to simplify functions and experiments. Functions and experiments. Okay, so what I'd really like to be able to do is, instead of looking at all of these, each one of these variables individually, what I'd really like to do is develop a, maybe one or two variables, or maybe three variables that describe the entire system. So maybe I can group these variables in such a way that then I can investigate the relationship of just those two variables. So I can break them down into dimensional groups or pi terms. Dimensionless groups, dimensionless products, or groups. For example, we will see that one thing we might be able to do is there are two dimensionless quantities we can use here, and we'll develop these shortly, that I could use d delta PL over rho v squared as one dimensionless term. So this would be one dimensionless term. And this would be some function of, so this would be one dimensionless term, d delta PL over rho v squared is some function of another term, rho vd over mu. And if you work through the units of these, you'll find that both of these are dimensionless. And I'm going to refer to dimensionless quantities such as these, at least those used for calculating and investigating functions and experiments, as pi terms. So this would be a pi term and another pi term. So I would derive these, I would consider these dimensionless units, and then instead of running through all the different combinations of variables individually, I would simply compare only this variable or this variable group or this dimensionless term against the other dimensionless term. So maybe on this axis I put rho vd over mu, and on this axis I put d delta PL delta PL over rho V squared. And I then go and find that there's some kind of relationship therein. So I'm going to use the, in this case I would use the 2 pi terms as I would perform an experiment just looking at those 2 pi terms and then develop a relationship that can be useful. So the nice thing about this is that I can just choose any pipe size and fluid that are easy to work with and vary V and see how PL transforms. Okay, so how did I get this? You may, if you want to, actually what I would suggest you do right now is, if you're watching this at home, stop this video and prove to yourself that each of these are dimensionless terms. D delta PL over rho V squared, and then rho VD over mu. So prove to yourself, so stop the video right now, and then go and prove to yourself that these 2 terms are dimensionless. Okay, so maybe you did stop it, maybe you didn't. Let's see whether you're feeling like listening to instructions, but that's okay. The next logical question is, okay, where did these come from? Did these just spring from the ether? Did they just come down from the mountaintop? How exactly did I know to write these particular dimensionless terms? So let us look at what we will come to refer to as the Buckingham PI Theorem. And this is discussed in section 7.2. Buckingham PI Theorem. So let's see what this means, or see what we can find here. So this is a methodical way, it's a very simple methodical way to find pi terms, or dimensionless numbers. To find dimensionless numbers, which again we refer to as pi terms. And there is a simple formula that determines how many pi terms we need to describe a system. Determines how many pi terms we need to describe a system. We need to describe a system. Okay, so the fundamental relationship here is that we're going to say that k variables, so our rho, our mu, etc., can be reduced to k minus r pi. Can be reduced to k minus r pi terms, or pi's. Pi apostrophe s, if you can't read my terrible handwriting. And of course you might then say, well, what? I mean, how does that make sense? I've defined how you find the number of pi terms, but I've done it by giving you yet another number that you don't know what it is, r. Well, thankfully r isn't too difficult to figure out. R is just a simple definition. R is the minimum number of reference dimensions. R stands for reference dimensions. In most cases, or in many cases, it's going to be 3, but it will depend on your particular problem. Min number of reference dimensions needed to describe the variables. Well, I cannot write. To describe variables. And what I mean by reference dimensions. So, if I go back up here, and I see that there are, if I look at the, for example, mu, it has m, l, and t. So I'm going to need, just for mu, I'm going to need 3 reference dimensions. the maximum number of reference dimensions is 3 for any given system, but again, this is going to describe the number of reference dimensions needed to describe all of the variables that you are using in your system. So e.g., if you have L, T, and M, then R is going to be equal to 3. So, let's see how something like this works. So, let's continue working through our previous example. For delta PL is some function of D rho, or D rho, mu, and V. And again, let's look at the units here. So for one, on the left over here, I'm going to do the MLT system, and on the right, I'm going to do the FLT system. So D, it helps if my D's look like D's. D is going to have units of L. Rho is going to have units of M, L to the negative 3. So we start by just listing out all of the fundamental dimensions, or the fundamental quantities or units of the of our variables here. Mu is M, L to the negative 1, T to the negative 1. L to the negative 1, T to the negative 1. V has dimensions of L, T to the negative 1. And delta PL, well, this is pressure per unit length, pressure drop per unit length. So this is going to have, if you work through this, you will find that it's M, L to the negative 1, T to the negative 2, T to the negative 2, L to the negative 1. Or M, L to the negative 2, T to the negative 2. And again, this is the MLT system. Then if I look at the FLT system, D, of course, has units of L. Rho, as we saw before, has units of F, L to the negative 4, T to the negative 2. V is going to have dimensions of L, T to the negative 1. Mu will have units of F, L to the negative 2T. And delta PL will have dimensions of F, L to the negative 2, L to the negative 1, pascals per meter, for example, equals F, L to the negative 3. And this here would be the FLT system. Would be the FLT system. Now, so let's find the number of, well, actually, before I do that, I would like to mention one thing. You can use whatever you're more comfortable with. You can use either FLT or MLT in your analysis, but it is very important to be aware that you do not mix. You should never have a problem and never have a system where you're having both F and M in there. That's going to destroy your analysis. It's going to cause you to select the wrong number of R terms. You'll probably have an impossible number like 4 for R, and that's not where you want to end up. So let us consider this. Well, let's look at these here. So let me first find my K. Well, my K is my total number of variables, and that's what's going to be here. So K is going to be equal to 5, which is just the number of variables. Which is just going to be equal to the number of variables. Then what about my R? Well, I can see here that I'm going to need both L, M, and a T. And it doesn't matter whether I look at the FLT or the MLT, there's clearly going to be all three of them here. So R, number of variables, R will be equal to 3, which is the reference dimensions. Number of reference dimensions. And so therefore, the number of pi terms is going to be equal to k minus r equals k minus r equals 5 minus 3, which is then 2. So what I'm going to end up with is sort of a pi 1 equals some sort of function times a pi 2. And this phi here is just referring to a function, like a function notation. So I'm going to convert delta PL as a function of 4 variables into one pi term, or one variable into a function of another variable. So basically what I'm able to do here is I am going to be able to greatly reduce the complexity of the problem using dimensional analysis. Okay, so that's well and good. Now that we know the number of pi terms, the next logical question, of course, is, well, we know that we need this number of pi terms. How on earth do we actually find these stupid things? And thankfully, I can teach you that. So, let's look at 7.3, determination of pi terms. Determination of pi terms. So determination of pi terms. So I'm going to use what's known as the method of repeating variables. Method of repeating variables. Method of repeating variables. So my steps are going to be, this is going to be a few steps, sort of a 5-step process. And I'm going to work through the example that we've seen previously, or I've been working with this delta PL example, and we're going to see exactly where these pi terms are coming from. So the first step is going to be to first list out all the variables. Makes sense? But they must be independent. So 1, list out all variables. But they must be independent. And now what do I mean by independent variables? What I mean by this is that they cannot be expressed as each other. They must be independent. Can't express one in terms of the other. Can't express one in terms of the other. In terms of the other. For example, if I were looking at a fluid statics problem, I wouldn't want to include both, say, density, mass, and volume of the system as 3 of my variables, because I can say that density is just mass over volume, so that wouldn't work out. Those are not independent variables. So delta PL, we suppose that this was a function of d rho. So there's a certain amount of guesswork at first to determine whether these are the only variables that are affecting the fluid flow. And we could probably imagine other things as well, such as maybe the roughness of the pipe. Although if you remember, the surface roughness of the pipe, the surface material, that kind of thing. Although if you remember early on, I mentioned that this was a smooth pipe. So we're kind of ignoring the surface properties of the material, although that would probably fit into that would have to fit into there somewhere. in most real-world systems. So mu and v, velocity v. We chose these, but now normally in most problems you're going to deal with, at least in this class, you're not going to have to worry about choosing these 5 variables. They'll generally be given to you. So, but what if I had a different set? What if I wanted to look at, what if what if I said delta PL is going to be a function of, what if I had 5 terms? D, rho, mu, nu, our other viscosity, and v. Would that work? Well, actually no, it would not. And that would not work because nu can be expressed as mu over rho. So these are not independent. Mu and nu and rho are not independent because they can be expressed in terms of the other. So therefore we cannot use these as a system. So again, or as a system of variables for our pi theory. Next, I wish to express each variable in terms of its basic dimensions. So to express each variable in terms of basic dimensions of its basic dimensions. Well, let's see, what do I mean by that? Well, we've already done this before. Delta PL is going to have units of, and I'm just going to do it for the MLT system, although you could just as easily do it for the FLT system. Delta PL has units of m, L to the negative 2, T to the negative 2. D has units of L. Rho, density, will have units of m, L to the negative 3. Mu will have units of m, L to the negative 1, T to the negative 1. And v will have units of L, T to the negative 1. So I get those. Then 3. So basically we've worked up through number 3 on previous slides. I'm just presenting all of this as a sort of unified series of steps. 3, I'm going to determine number of pi terms. Determine required number of pi terms. Number of pi terms. So in this case, I find that k minus r, and just as we did previously, is equal to 5 minus 3, which is equal to 2. Then I'm going to select r repeating variables. R repeating variables. And what do I mean by repeating variables? Well, let's think about this. Select R repeating variables. Let's go back up to some of the previous slides and look where we defined this here. So if you look at this, D and D, rho and rho, V and V, these occur in all of the pi terms, or in both of the pi terms in this case. So in our problem here, these are repeating variables. Repeating variables are ones which occur in all of the pi terms. So there are some rules for determining these repeating variables. And we're going to need R number of them. So first, A, you do not want to include the dependent variable. We do not want to include the dependent variable. So delta PL can't be one of our repeating variables. Delta PL, within your set of repeating variables, all reference dimensions must be present. All reference dimensions must be present in your set of repeating variables. Must be present in the repeating variables. In the repeating variables. In the repeating variables. In this case, since we're using M, L, and T, in whatever variables we choose, M, L, and T must be up here at least once. And that doesn't mean that they have to, we can only use variables that a single variable has M, L, and T in it. It just means that among the total set, M, L, and T must appear at least once. At least once. M, L, and T must appear at least once. C. Each must be dimensionally independent. What does that mean? Each must be dimensionally independent. We'll see that. Must be dimensionally independent. Independent. What we mean by that is, can it be combined to form one? In other words, we can't combine our repeating variables together to cancel each other out, essentially. Cannot be combined to form one. So we can't combine them together, they're not equivalents of each other. To form one. Or our repeating variables cannot form a dimensionless number. So I shouldn't be able to manipulate them in order to form a dimensionless number. A dimensionless number. Okay, so let's look at some examples here. Cannot form a dimensionless number. So let's look at some potential repeating variables. I have a few potentials I could look at. I could look at, what if I did, say, D, mu, and V? Well, this has units of L, mu has units of M, L to the negative 1, T to the negative 1, and V has units of L, T to the negative 1. So, let's think about this. Well, it does satisfy A. We didn't use delta PL. All reference dimensions are shown, in other words, M, L, and T. If we look at these, there doesn't appear to be any way to combine these together to cancel each other out, to form a dimensionless term. In other words, I can't multiply and divide them by each other to get a dimensionless number. So this is a good potential candidate. Also, I could say, well, there are some other options. What if I looked at D, rho and B? Rho and B, would that work? D, rho and B? Well, D has units of L. Rho has units of, or dimensions. I shouldn't be saying units, I should be saying dimensions. Is probably the more proper term. M, L to the negative 3. And V has velocity has dimensions of L, T to the negative 1. Would this work? Well, we don't include the dependent variable, we can't combine them together, so yes, this would be okay as well. This is okay. This one's okay. Let's see what else we could do. d rho, and mu would be maybe perhaps 1. This one would have units of L, or sorry, dimensions of L. This one would have dimensions of m, L to the negative 3, and mu would have dimensions of m, L to the negative 1, t to the negative 1. And this will work because as well, if we see here, there's only one t term, so there's no way that I can cancel this out, because this is the only one, this term is the mu is the only one that has a t in it. So there's no way I can manipulate this to cancel out the t that's already there. So that would work. And so the takeaway from this is that there's different possibilities. We can have multiple different possibilities. There's no one right answer. We can have different systems that would produce dimensionless numbers. That would not be able to produce dimensionless numbers by combining them together. So there's several excellent candidates for a set of pi terms. What if we tried something different? Suppose we had something like sigma, maybe m, L to the negative 2. Mu, sigma isn't one of our variables, let's say we did have it. Mu, m, L to the negative 1, t to the negative 1. And v, units, dimensions, v, L, t to the negative 1. Would these work as potential repeating variables? Well, let's see. What happens if I do sigma over mu v? That's going to give me 1. So this one would not work. This fails criteria C. It's dimensionless. Or it can be combined together in a manner in order to form a dimensionless quantity. And this can be tricky. So these does take time. There's, not just one quick method I can say, oh, do this. This is something that does take time. You just have to explore different possibilities, and often it can somewhat depend on how you want to set up your experiment. But let's just say for now, for whatever reason, I want to, and in terms of why these work dimensionally, well, this one works because m can't cancel. Why we can't form a dimensionless with these? Well, this one m can't cancel. Here, t can't cancel. And then here, t as well can't cancel. So a good criteria, or a good giveaway that these would work as a set of repeating variables. A set of repeating variables is if you have a dimension that only appears in one pi term. There's no way to, or only appears in, I should not say in one pi term, only appears in, where you have a dimension that only appears in one of your variables. There's no way to cancel that out if that dimension does not appear in other variables. So, you know what, just for brevity's sake, let's just say I want to go ahead and use this one here. I'm just going to pick this one for no particular reason, just maybe this would be the most convenient for whatever reason. So let's just say I use this one. So next, I want to form repeating variables, or once I have my repeating variables, I want to form my pi terms. Form pi terms. And what do I mean by this? Well, I multiply the non-repeating variables. Non-repeating variables to get dimensionless numbers. Multiply non-repeating variables to get dimensionless numbers. Each non-repeating variable is going to have its own pi term. To get dimensionless numbers, and so A and B here, a few rules. You can raise the repeating variables to any power repeating variables can be raised to any power, positive or negative. Well, positive or negative whole number, any integer basically. By any power. And B, the non-repeating variables must have a power of 1. Variables must have a power of 1. Power of 1. So I'm going to start by listing out my repeating and non-repeating variables here. So here, my repeating variables I have my repeating variables and my non-repeating variables. So, again, I'm going to list them out along with their dimensions. So D, diameter, has dimensions of L. Rho, density, has dimensions of M, L to the negative 3. Velocity, V, has dimensions of L, T to the negative 1. Delta PL has dimensions of M, L to the negative 2, T to the negative 2, and mu has dimensions of M, L to the negative 1, T to the negative 1. So I'm going to start with the first pi term. Start with pi 1. In the next lecture, we'll discuss a more sort of systematic way of getting these powers. Well, and basically, I just need to sort of play with these until I get something that's dimensionless. So I could say, well, delta PL has dimensions of M, L to the negative 2, T to the negative 2. Then I could say, oh, delta PL over rho. And why would I do this? Well, if I look at rho, it has a mass, and this one has a mass, so maybe I can start by dividing these. So if I'm going to create a pi term with delta PL in it, I know the delta PL is non-repeating, so it's going to be in the numerator of power 1. And rho is the only thing with a mass in here, so it has to be in the denominator. So I'm going to apply that one first. And this would get me M, L to the negative 2, T to the negative 2, over M, L to the negative 3. And so the m's would cancel out, and then I would have T to the negative 2 over L to the negative 1. Alright, then what happens if I multiply, I continue this by multiplying by, say, D. If I throw a D in here, delta PL over rho times D. Well, that'll cancel out the length. So I will have T to the negative 2 over L to the negative 1 times L, and, well, actually, no, it won't. I'm an idiot, never mind. The problem with that is, if you're not paying attention, you'll see, you'll think that this is, oh, that's over L. That won't work at all. What this will actually reduce to is L squared T to the negative 2. Oh no, we haven't done anything right? We've actually got it more complicated. Or have we? Let's think about this. This is L squared over T squared. Well, that's just equal to V squared. This has the same dimensions as V squared. So, so basically I could say delta PL over rho times D is equal to V squared. Or if I put this in dimensionless, I could just reduce this to pi 1 is equal to delta PL D over rho V squared. And that would be my pi 1 term. Delta PL times the diameter over rho times V squared, and that becomes my first pi term. Then for pi 2, well, let me start with mu equals, or has dimensions of L to the negative 1, T to the negative 1. Then I'll divide by, again, because mu is going to be my non-repeating variable, so I just want to start with it. It's going to be the non-repeating variable for this pi term. And then I'm going to divide by rho, because that's the only other thing with a mass in it. So that's going to get me L to the negative 1, T to the negative 1, over L to the negative 3. And so my mass cancel out, and I'm going to get T to the negative 1 over L to the negative 2. And that becomes L squared over T. Next, I'm going to have, so I have L squared over T, and what might I do? Well, let's experiment with this and say, what happens if I throw a V in there? What if I divide by V? So mu rho V over rho V. Now, this is kind of, what I'm showing you right now in this lecture is going to be more sort of trial and error methods. But in the next lesson, we'll see how to sort of use systems of equations to solve for these powers directly. But L squared over T times 1 over LT to the negative 1. That's our velocity. And so this one then is just going to give me L. And then finally, I can get rid of that L by just dividing by our diameter D. Rho dV equals L over L, which is just 1. Dimensions, dimensions, dimensions. So I see now that pi 2 is equal to mu over rho dV. So where would this come down to, or what this would come down to is I would have a relationship. I'm going to use these two pi terms to then investigate my problem. Instead of running an experiment with many, many, many different variables, many experiments, many different variables, many different pipe diameters, all of that, I'm going to look at just these two variables, or these two pi terms, and compare them in relation to each other, and find a function therein, relating them through a very simple experiment. So I'm basically going to say that delta PL times D over rho V squared is going to be some function of mu over rho dV over rho dV. Or I could also say that because these are dimensional, or because these are dimensionless quantities, it actually doesn't matter which of, on the right side at least, it doesn't matter which is in the numerator. So over here I want to keep my independent variable in the numerator, so I'm not going to flip this over rho V squared. But I could just as well say that this is a function of rho dV over mu. So we've taken 5 variables and reduced them to 2. Five variables down to 2, and this reduces the number of experiments that we need to run. And again, this reduces the number of experiments we need to run, makes our analysis much simpler, and makes experiments and analysis and systems that would, or the analysis of systems that would otherwise be prohibitively difficult and expensive to experimentally investigate, into something that we can actually practically do. Alright, so hopefully that was a useful introduction to pi terms, and we will continue on this in the next video. And so thank you as always, and goodbye.